Welcome to the lectures on modern digital communication techniques. Till now we have discussed different source coding techniques where we have assumed that there is a discrete source, and we have seen various methods by which source can be compressed, or the signal rate at which things are coming out from the source can be represented in a better way, and this we have termed as source coding. And the reason why we should do source coding, we have said before through an example that source coding, it helps in compression. So, even today various techniques are being tried so that you get a better output from the source, better in the sense lower bit rate. Now, why this is important? This is important so that in order to estimate minimum bit rate or the capacity, this term might be clear later on, a channel must provide for reliable communication. Okay. So, when we write this, what we actually mean is that we are estimating the rate at which bits can come out from a source. So, suppose we have estimated that on an average we require 1.5 bits per source symbol, and the source generates, let us say, 1000 symbols per second. So, that means you need to have the rate at which bits come out from the source is 1.5 kilobits per second. At this point, to have a reliable communication between the source and the destination, you would require the link between the transmitter, that is the source, and the receiver, that is the destination. So, there lies the channel between them, right. So, this should be able to carry that data rate through this channel. Now, suppose example, the transmitter produces, let us say, 1.5 kilobits per second, whereas the channel capacity is 4 kilobits per second. This implies that there will be errors which will be, this implies there will be errors which cannot be reduced, that means you cannot make it 0. However, if the channel capacity is, let us say, 1.55 kilobits per second, this implies that one would be able to achieve, theoretically at least, error free communication. Okay, by this I mean communication. So, what it means is that suppose I have a channel for which I know a capacity. Now, when I would like to send some source through this channel, I would be tell a priori whether I will be able to get error free or reliable communication through that link or not, right. So, this is one of the important things that we can get when we study source coding. So, and a typical number which we use, we can compare, is the entropy of the source. The entropy of the source we have calculated is given in bits per source symbol, multiplied by the symbol rate gives us bits per second, and we also will get channel capacity in bits per second. So, if we get H x and we compare C of the channel, we should have H of x should be less than C of the channel, right. If this is not true, you are going to get errors. If this is true, then you can establish a reliable communication. Now, with this we move further, and what we now take at this point is, with the background of your analog communications, that how would one get discrete output from sources which are analog in nature. For example, the voice or the speech or music. So, example, I have this microphone over here. So, when we are recording the voice signal, then how do we get it converted to discrete source, or this analog source should get converted to a digital discrete source, so that we can use the techniques that we have studied before. So, to do this, we usually convert the analog signals is first converted to digital form, and definitely at the receiver you would like to convert this digital form back to analog. So, this particular process is usually described by the terminology analog to digital conversion. That is what we are going to discuss in this particular lecture. So, this analog to digital conversion, we have seen a picture before. So, has 3 steps. The first step is the sampling, and the input signal is x analog of t, which we can say is the analog signal. Then this sampled signal, which we can represent by x n, or the discrete time signal. So, this is still continuous in amplitude, but discrete in time. So, if we have some waveform like this, and then we would have to have a quantizer which we will see in the later discussion. So, at the output of the quantizer we have x q of n, which is representing q representing quantized. So, you have quantized signal, and this quantized signal is then passed to the coder or the encoder, which converts this to the digital signal. So, we will discuss about this particular sampling, which takes an analog signal, it samples the signal and it converts it into a discrete time signal. This analog to digital conversion or this sampling can be done in many ways. So, the one that we are going to consider is called periodic sampling, or it is also called uniform sampling. So, this is what we will restrict ourselves, and this can be established by the relationship that x of n that we have over here is equal to x a of n of t, where n lies in the range minus infinity to plus infinity, and x a of t has been sampled. So, x a of t has been sampled at every interval of t seconds. So, every t seconds we are taking samples of it. So, that means, if there is an analog signal, we are going to take samples at every fixed interval. So, this interval that we are talking about is t in our expression. So, x 1 is x analog at time instant t, x 2 is basically the analog signal at time instant 2 t. So, if this is 1 t, 2 t, 3 t, and this is time, so multiplied by t. So, this is the way we get the x n from x a of t, and we also have the relationship that 1 upon t is equal to f s, which is called the sampling rate. Or samples per second. So, through this we can get the analog samples, but at discrete time. So, this is also called the sampling frequency. Just briefly, let me tell you at this point that these particular details you can easily capture on a course on digital signal processing or discrete time processing, where one of the initial things that one learns is about analog to digital conversion. So, here we will take a cursory look into the principles which govern this particular operation. So, for this generally what you can think of is there is this analog signal x a of t, and then there is this sampler which is usually represented by a circuit like this. That means, it closes, there is a RC circuit you can imagine, and that can hold it, and this switch closes at a rate f s equals to 1 by t. So, this is a typical representation of a sampler, and what you get produced is x n, which is nothing but x a taken at intervals of time, which is integer multiples of capital T. And the signals that you have here is, we have already drawn it. Let us say this is t, this is x a of t, and here what you get, you will have n, and you are going to get the same signal, but sampled version. Let us say we sample at these intervals. So, this is t, this is 2 t, this is 3 t, and so on and so forth, or this interval is 1, 2, 3 and so on. So, this happens at a time when this is equal to t, 2 t and so on and so forth, and this is usually denoted as x of n. So, to understand this better, let us take x a of t is equal to a cos 2 pi f t plus theta, where f is the analog frequency of the signal. So, this could be also related to the discrete frequency, which we will see as f. So, we have to establish the relationship to the discrete frequency f through this kind of a relationship. So, what we see is that since f s is equal to 1 upon t, what we could write is that x a at n t is basically x of n, which is a cos 2 pi f. So, at n t, so t gets replaced by n t plus theta. Now, since f s is equal to 1 by t, this you get as a cos 2 pi will replace f, n t remains n t as, sorry, will replace t by f times n upon f s, or f by f s is the ratio that we have. So, what we usually write this as further a cos 2 pi, and for convenience we would write it as n f plus theta, where f is equal to f by f s. Now, this is the important relationship that we have between x a of t and x n of t, related through f s and f and 1 upon n t. So, f that we have over here is this f that is used over here in these two expression is known as the relative or the normalized frequency. This is clear because you have capital F over small f. So, this f is relative to this particular sampling frequency. Now, since this is a ratio, what you can guess from this is that for certain values of f which is less than f s, we have this f lying between to be less than 1, and when f is more than f s, we get the value of f which is greater than 1. So, because of this kind of a relationship, we have certain constraints on the values that f and f s can take, and that will be clear very soon. So, suppose at this point we say that x A of t is equal to A cos 2 pi f 0 of t plus theta. That means, I have taken a particular value of frequency instead of a generic value that we have taken here. So, if we take this as 2 pi f 0 t and we decide that f s is equal to 1 by t, we can easily write that x n using our previous relationship, that means the relationship that we have over here. So, since f is replaced by f 0, our small f would also get replaced by small f 0, a cos 2 pi small f 0 n plus theta. So, what we see is that there is a lot of similarity in these relationships in these two expressions. However, t is getting replaced by the index n, which is here on the left hand side, and capital F 0, which is in hertz, is getting replaced by f 0, which is in the digital frequency domain, and f 0 is equal to f 0 upon f s. Now, at this point, it is interesting to note is that if f 0 is so basically we can find f 0 given small f 0 if we know this particular sampling frequency. However, there is a little issue with this particular description, is that suppose instead of taking this particular signal, we take another signal or a generic family of signals, which we can write x a of t is equal to cos 2 pi f k of t plus theta, where we define f k to be equal to f 0 plus k times f s. Now, suppose I take this particular signal instead of taking f 0. So, where f k is f 0 plus an integer multiple of f s. So, of course, I should mention that k is equal to plus minus 1, plus minus 2, and so on and so forth. So, what would happen as a consequence of this? As a consequence of this, you are going to get x n is equal to x a of n t, which is equal to a cos 2 pi f k I am replacing by this expression, f k I am replacing by this expression, and t of course is replaced by n upon f s, because t is equal to n times capital T, and capital T is equal to 1 upon f s plus theta. So, this results in a cos 2 pi n f 0 upon f s plus theta plus, let us look at this, 2 pi n, we have 2 pi, we have n, and k, because f s and f s cancels out. So, this is what remains, which is equal to a cos 2 pi n f 0 plus theta. Now, if you look at this expression and if you look at this expression, if I mark this as let us say 1 and if I mark this as 2, 2 is equal to 1, because there is a 2 pi n k, n is an integer and k is an integer. So, we have multiple of 2 pi. So, since we have multiple of 2 pi, cos of theta plus 2 pi is basically cos of theta. So, we have this expression. That means, you cannot distinguish between this sequence that we generate at this point. So, that means, if we recall this particular picture, we have x a of t here and we have x n over here. So, all we have established is, if I have fixed a sampling frequency, let us say f s, then there could be multitude of different analog signals which could become the same discrete signal. So, this kind of a situation is usually known as aliasing, because x n is an alias of many different sinusoids. One of them could be f0 and others could be f0 plus integer times the sampling frequency. So, you are unable to distinguish between one signal and another signal which could be of different center frequencies. And the reason for this is quite clear from the expression which is here, which basically establishes that f, which is the digital frequency, is basically a ratio of f times f s, and since we are aware that if you try to map the analog frequency to the digital frequency, what you are going to get is there is a linear relationship from capital F to small f for f s by 2 to minus f s by 2, but thereafter it repeats, thereafter it wraps around. So, because of this we are unable to distinguish between the frequency here and the frequency here and the frequency here. So, at this point what we get is the important notion of the sampling theorem. This is a very important theorem which comes from the above description. What it says is that if the highest frequency contained in any analog signal x a of t is f max, which is equal to b, and the signal is sampled at a rate f s which is greater than twice f max, which is equal to 2 b, which can be defined as 2 b, then x a of t can be exactly recovered from its sample values, that is x n, using the interpolation function g of t is equal to sine of 2 pi b t upon 2 pi b t. So, that means that if we have x a of t, so we can use this particular sheet again, which tells that what we see over here is x n is identical for different values of capital F k. So, that means if we have a signal which goes like this, and suppose we have another signal, sorry, I should have the full swing like this, which is an integer multiple of this original signal. In that case, the samples that it produces, one will not be able to reconstruct the original signal, because all of them map to the same discrete sequence, if you look at it. So, they all map to the same discrete sequence. However, what it says is that if you know the maximum frequency content as f max, so that means if we go back to this signal, if I know the maximum value of f k which is present in this signal, then we should choose our sampling frequency f s, which is 2 times the maximum sampling frequency, and if which is more than 2 times, and if you are selecting your sampling frequency which is more than 2 times the maximum frequency, then you can reconstruct x a of t, x a t, that means the analog signal, exactly without aliasing, and that you can reconstruct using g t, which is expressed by sine of 2 pi b, b which is equal to f max upon 2 pi b t. In this case, x a of t, that is the analog signal that you have, can be expressed as n is equal to minus infinity to plus infinity x a of n upon f s, because f s is f s 1 upon f s is t. So, basically x a of n t times g of t minus n upon f s. Again you can, instead of this, you can look at it as x a of t is equal to sum of n equals to minus infinity to infinity x a of n t g of t minus n t. So, of course, we have said that x a of n by f s we should write is x a of n t, which is equal to x a of n, which are samples of x a of t. So, in this way what we have established is that if you are sampling a signal to convert it from analog form to a digital form, then one should choose a sampling frequency which is at least twice or more than 2 times the sampling frequency, 2 times the maximum frequency. So, if you are doing it, then you would avoid aliasing. What we did not do in this particular discussion is we did not prove that more than 2 times is sufficient to reconstruct a signal exactly without aliasing. We will not take it up as part of this course, because that is usually handled in part of discrete time signal processing or digital signal processing communications. In the next lecture, we are going to discuss about how to take these discrete time signals. That means, we have the signals at this point. Now, we have the signal at this particular point. So, we have been able to do this. So, what we have said is, suppose I know the frequency content. That means, for this, if I know the frequency content or I know the f max, then I will choose f s as greater than twice f max. Then I can generate this signal, and these signals will not be aliased, and this thing comes from the sampling theorem, so that we can reconstruct it back to its original form, which is required at the receiver. At the receiver side, you will require this. That means, at this end you are going to require this. So, basically what we have ended up is why we need at least this kind of a relationship, otherwise we are going to end up in aliasing. And now, since we have got these discrete time signals which occur at discrete intervals, but take continuous values in amplitude, we should now discuss about how to quantize this, or what is the meaning of quantizer, so that we get a sequence which is a binary sequence which can finally go into the encoder, and some of the encoders we have actually discussed in our earlier lectures. Thank you.